Welcome back. This is the second part of section 2.1, in which we are going to prove the analytic form of the Hahn-Banach theorem. The proof uses Zorn's lemma from set theory, and this is why we started chapter 0 with a review of this important tool for proving, which is proving existence results. Okay, so consider the set capital P of all linear functions h, each one of these functional being defined on a subspace that we call D of h, the domain of h, which is the subspace of E, that contain moreover the subspace G. So we have five things actually. So each h is linear. It's defined on its own subspace. So the domain varies from function to function. But all of these domains contain the subspace G, and H extends G and satisfies the inequality that h of x is less or equal than the subnorm P of x for all x in the domain of H. Okay. Now, on this collection or this set of linear functionals, we put an order relation. So we say that H1 is related to H2 if H2 extends H1, so the domain of H2 contains the domain of H1, and H2 coincides with H1 on their common domain, which is the domain of the smaller one. Okay. So first of all, this set is non-empty because trivially G is less or equal than itself. Because G, in some sense, we can say that G extends itself in a trivial way. Okay, because here we put less or equal, so it's not really strictly less. Now we claim that P is inductive, which means once again that any totally ordered subset of P is bounded from above with respect to this order relation. Okay, and we gave this as an example, as a fundamental example of order relation between functions. Okay, so consider a subset Q of P, which is totally ordered with respect to this extension relation. Now, so Q is a collection of functions, so we can write it as a family, H sub I, where I runs in some index set I. So this is convenient, but not necessary, so we can do without it. So now we define a functional H as follows. What is the domain of H? The domain of H is the union of all domains of elements in Q. So this is the domain. Now, how do you define h of x? Okay, if x is in the domain, which is the union, then x is by definition belongs to one of these domains, dhi. So we set h of x equal hi of x. Now we have to check something here. What if x belongs to two different domains, dhi and dhj? What happens? So we have to make sure that this makes sense. So it's well defined. Okay, suppose that x belongs to dhj for another index j. Now, since Q is totally ordered, then either hi extends xj or hj extends hi. Okay, so this is the assumption of total ordering. So, but in either case, hi of x equal to hj of x, because x belongs to both domains. Okay, and if one extends the other, they agree on their common, the smaller one. Okay, the intersection is actually either dhi or dhj. So this really makes sense. So h is well defined, so it doesn't depend on the index. Okay, so here we used crucially the assumption that Q is totally ordered, because if we take an arbitrary set which is not totally ordered, this is not necessarily true. Okay, so let us check that H belongs to the set P, and it will be clear that actually it's clear from the definition that H is an upper bound of P, of Q. Okay. So first of all, we have to check, so the 5 things that define belonging to P. So first of all, the domain of H as we define it is subspace of P. Okay, it's not totally clear why, because D of H is the union of domains, of subspaces. But why is it itself a subspace? The union of 2 subspaces in general need not be a subspace. But here, because you have the total ordering assumption, is true. How do we prove that DH, the domain of H, is a subspace of P? Okay, so I have to prove 2 things. If it's stable under addition and stable under multiplication by scalars. So pick an element x in the domain and a constant lambda in R. Now, by definition, x belongs to some domain of hi for some I, but dhi is a subspace by definition. So lambda x belongs to dhi. Okay, but dhi is contained in dh because it's the union. So we proved that dh is stable under multiplication by scalars. Now, what about the sum? Consider 2 elements in the domain of H. Then, by definition, x belongs to some dhi and y belongs to another dhj. But since Q is totally ordered, either hi extends the hj or vice versa. Okay, so the 2 cases are symmetric. So suppose that dhi is contained in dij, which means that hj extends hi. Okay, then both x and y belong to dhj. Okay, but dhj is a subspace of E, so it's stable under addition. So the sum belongs to dhj, which is a subset of dh. So we took 2 elements in dh and proved that their sum is again in dh. So this is the first point, that dh is really a subspace of E. Second point, the domain of H contains the subspace G, on which small g is defined. This is also by definition, because by definition of the set capital P, each hi in Q contains the subspace G. So the union contains G, because the H is the union of the hi. Now, by definition of H is an extension of each hi, because h of x is equal to hi of x if x belongs to the hi. So it's an extension, so it's defined on a bigger domain. Okay. Now, since each hi extends G, then the extension of the extension is okay. So, and fourth point, H is linear. This is kind of trivial. So I take 2 elements in the domain of H and a constant lambda in R. Then x belongs to some dhi, and therefore, since we proved that dhi is subspace, lambda x belongs to dhi, and so h of lambda x by definition is hi of lambda x. This is by definition of H. But hi is linear, so we can put the lambda outside. And hi of x is equal to h of x also by definition. So h of lambda x equal lambda h of x. Now, the other y is in some dhj. So, and since Q is totally ordered, so either dhi is contained in dhj or vice versa. So suppose that dhj contains dhi, then both elements are in dhj, which is a subspace. So the sum of x and y is again in dhj, and therefore, by definition of h of x plus y is equal to hj of x plus y. But since hj is linear, then hj of the sum is the sum of hj. But since both x and y are in the nj, that then hj of x equal h of x and h of y equal h. So have linearity. And final point, the inequality. So take x in the domain of H, then, as you know, x is in some dhi. But since hi belongs to the collection P, and by definition, each element of P satisfies the inequality, so hi of x is less or equal than P of x. But by definition of h of x equal hi of x. So h of x is less or equal than P of x. So this is, everything is trivial. So Okay, so we proved that this H belongs to P, and it extends each HI by construction. So it's an upper bound for Q. Okay, now I'm not saying that H is in Q, we don't know that, but it's an upper bound, okay, in the sense that any element in Q is less or equal or is extendable to H. Okay, so H is an extension of each element of Q. Okay, so this proves that the set P is inductive according to this order relation. So now we can apply Zorn's lemma, and which tells us that there is a maximal element that I call F. And what is a maximal element here? It means that it is not strictly less than another element in P. So it means that it's non-extendable. Okay. So it extends G by construction, but it's itself non-extendable. Okay. This is the meaning of maximality. Okay. So if we prove that the domain of F is the whole space E, then we are done. Okay. Because then by definition F extends G to the whole space and satisfies the inequality because it belongs to P. Okay, so we reason by contradiction. Suppose that dF is not the whole space. So dF is strictly contained in. Therefore, we can find an element in x0 in E, which is not in the domain of F. Okay, now we'll get a contradiction. But before this, we prove another claim. This inequality. For every x and y in the domain of F, we have f of y minus p, the subnorm of y minus x0, is less or equal than p of x plus x0 minus f of x. Okay. Why this is true? Okay. Since f is linear, the f of x plus f of y is f of the sum. But since f is in p, in capital P, it satisfies the inequality. So f of anything is less than p of the argument, same argument. But since P is sublinear, we can write x plus y as x plus x0 minus x0 plus y. So this is the triangle inequality, if you like. So P of x plus y is less than P of x plus x0 plus P of minus x0 plus y. Okay, and therefore, if I subtract P of y minus x0 and subtract f of x, I get f of y minus P of y minus x0 is less than P of x plus x0 minus f of x. And this is true for every x and y in the domain of F. So we proved the claim. Okay, so since this is true for any y and any x, if I take here the supremum over y is less than the infimum over x here. Okay? Because any element, this is something almost trivial. Okay? Because if fixed y, this is true for every x, so this is a lower bound, but inf is the biggest lower bound, so this is less or equal than the inf. But y was arbitrary, so for every y, this quantity is less than the inf. Therefore, the inf is an upper bound, but the sup is the smallest upper bound. So the sup of this guy is less than the inf of that guy. And therefore, we can take a number alpha in between these two, supremum and inf. Okay? Or if you like, the other way around, because you can also say here sup of f of x minus p of x minus x0, x in df, same thing, because now x and y are dummy variables. So you can put f of z minus p of z minus x0, z in df. Okay, so if you look at this inequality, alpha less than p of x plus x0 minus f of x. So we add f of x, we get f of x plus alpha less than p of x plus x0. And if you look at this inequality, so write it f of x minus p of x minus x0 less than alpha, and then subtract alpha and add p of y minus x, or p of x minus x0, we get this inequality. And now, last claim, for every t in R, f of x plus t alpha is less or equal than p of x plus t x0 whenever x is in the domain of F, and for every t in R. So I split this to prove that I distinguish between two cases. T equals 0 is trivial because if t equals 0, this just reduces to f of x less or equal than p of x, and this is by definition because f satisfies the inequality. If t is positive, we apply this inequality, but instead of x, x over t. Okay, so we write, so according to 1, the first inequality of 1, f of x over t plus alpha is less or equal than p of x over t plus x0. Now, since t is positive, I multiply everything by t. So since f is linear, when I multiply by t, I get f of x, and here I get t alpha. And here I get Tp of something, of this guy. But T is also positively homogeneous. So T of P is P of T of this. But when I multiply T inside, I get X plus Tx0, and this is precisely that. Now, if T is negative, I use this inequality. But I put instead of X minus X over T, which is still in the domain. So same thing, but I multiply by minus T, which is positive, and I get the same thing. Okay. Okay, fine. And now we are almost done. We define a new functional phi, which is defined on the domain of F, direct sum the vector space, the one-dimensional vector space generated by x0. So any element, if I consider this direct sum, now this is of course a subspace, some direct sum of two subspaces, because x0 is not in the F. Okay, so this is strictly big. So how to define phi? Any element in df plus rx0 can be written as x plus an element here, which is of the form tx0. So we put phi of x plus tx0 is f of x plus t alpha. So it's very easy to check that phi that we define in this way is linear. And it's an extension of f, because when t equals 0, I get phi of x equal f of x. So this is actually the contradiction. Okay, so now we have an extension. So if we, but we have to use this inequality actually. This inequality tells me that phi of x plus t alpha is less than p of x plus tx0. So phi satisfies the same inequality. So if you like, we can put phi of z is less or equal than p of z. Okay. So this means that this new function phi belongs to the collection P that satisfies the 5 properties. So, but this contradicts the maximality of f, okay? Because f was maxima, so it cannot be extendable to a strictly bigger. So this contradiction proves that x0 is, so the assumption that df is different from E is not true. So df is equal to E, and we are not. So this concludes the proof and the video. Thank you for your attention, and see you next time.